Okay, thanks, Chris, and thanks, Ted. So as Chris just mentioned, deployment on multi-core CPUs should make software faster by enabling our tasks to run in parallel rather than waiting for a time slice on a single core. But in practice, parallel processing on multiple cores can introduce contention for system resources and therefore make the application slower than it was when it was deployed on a single core. So achieving multi-cores hoped for linear performance gains hinges on resolving these issues. Now, we're never really going to get to linear performance gains, but we like to get as close as possible. So I'm going to discuss a couple of examples of these types of conflicts and solutions that can be applied when facing these issues, or at least provide the conceptual starting point for solutions to similar conflicts. The first example of resource contention in multi-core, multi-threaded systems involves the C and C++ heap. In a multi-threaded application, the heap is a shared resource, and the solution to avoiding contention for that shared resource is a custom memory allocator. The second conflict is contention for updating shared data, and its solution that we'll present is called multi-version concurrency control. Now, normally, the C runtime library provides malloc and heap, or C++'s new and delete, that allow applications to allocate memory from the heap and release memory back to the heap. Excuse me, application developers, we tend to use these functions liberally without really thinking about how they actually work. As an interesting side note, there's an interesting discussion on Quora. Ted's going to put the link to the website on the chat window here in a moment, where there's a discussion going on about whether or not dynamic memory allocation should even be allowed in embedded systems. Some really good points being made there. I'll point out that the solution to this resource contention that we're going to talk about today, the custom memory allocator, avoids the issues that are being discussed on that quorum discussion page about whether or not dynamic memory allocation should be allowed in embedded systems. Okay, so what's going on inside malloc is that the heap is organized as a pool of contiguous memory locations that we also call freeholds, and that are referenced by a singly linked chain of pointers. The allocator services a request for memory allocation by walking that chain of pointers looking for a large enough freehold. When a freehold is located that's large enough to satisfy that allocation request, then it's unlinked from the chain. And if the freehold is actually larger than the actual allocation request, then it's divided into the requested allocation size and the remainder, and then that remainder gets linked back into the heap's chain of pointers. And then, of course, the allocated chunk gets sent to the application. Otherwise, if that freehold was exactly the right size, then the chain is just going to be updated to jump over that just allocated memory. In a multi-threaded application, the allocator's chain of pointers is a shared resource that has to be protected. Chaos would follow if the thread that is in the process of breaking the chain to insert a new link was interrupted by a context switch, and then another thread tried to walk that now broken chain. So to prevent that circumstance, the chain is protected by a mutex to prevent concurrent access and therefore preserve the integrity of the allocator's metadata. Now, on single-core systems, the latency that's caused by that locking is minimal because the CPU is going to be kept busy by processes that are unrelated to memory management. On a multi-core system, though, all but one core might be idle with respect to the utilization of the shared resource. In other words, if the application was doing nothing but allocating and freeing memory, then the threads would be serialized due to that mutex. So the extent of this problem for any particular application is going to be directly proportional to the amount of time that the application is doing dynamic memory management. In other words, allocating and freeing memory. Now, being an in-memory database, this was actually a pretty important issue to us because in-memory databases are always allocating and freeing memory, not necessarily through malloc and freeze, we'll see, but within our own free pool. Okay, so here we're trying to illustrate that problem with a diagram. So you've got the heap with its chain of pointers in the middle, and on the top and the bottom are a bunch of threads that all want access to the heap to either allocate or free some memory. And because that chain of pointers has to be protected by a mutex to preserve the integrity of the allocator's metadata, those threads' access to the heap end up being serialized, and the potential for parallelism on a multi-core system is effectively defeated. The threads have to line up and take their turn one at a time with the heap. So given that the heap has to be protected, what can we possibly do to break that serialization? Well, one possibility is to avoid dynamic memory allocation altogether, as that article on Quora suggests. But especially in embedded systems, the stack size is often very limited, and then you also sacrifice the flexibility that dynamic memory allocation provides, such as the ability to allocate memory in one task that's accessible by another task that's executing in parallel. A more effective solution that doesn't sacrifice the advantages of dynamic memory management is to create a custom memory manager that largely avoids the need for synchronization by providing separate memory allocators for each thread so that each allocator manages memory independently of the others. This approach is what we call a thread local allocator. Our implementation of a thread local allocator is based on a block allocator. The thread local allocator is based on the same concept as thread local storage, which you're probably already familiar with if you're already writing multi-threaded application code. So as I said, our implementation of the thread local allocator uses a block allocator. A thread local allocator doesn't have to use a block allocator. There's a gajillion different types of allocators out there. There's block allocators, bitmap allocators, stack allocators, and so on and so forth. It just so happened that a block allocator suited our purposes because in-memory databases, the storage arena for an in-memory database is always divided up into some number of fixed-size pages, and those fixed-size pages tend to be pretty small, typically 256 bytes, give or take 100 bytes. So it fits with a block allocator very well. Now, the block allocator differs from malloc in that most implementations of malloc are based on what's called a list allocator. So we need to understand a little bit about a list allocator to understand the advantages of a block allocator. So a list allocator has two kinds of metadata: the chain of pointers that we talked about earlier, and the size of the free hole. So every free hole on a 32-bit system is going to have 8 bytes of overhead. You got the chain pointer, which is 4 bytes, and the size of the free hole, which is another 4 bytes. So as the heap gets allocated, large free holes get divided up to serve smaller allocation requests, as I described earlier, and that's the essence of fragmentation. List allocators try to minimize fragmentation by adjoining adjacent free holes. In other words, if 10 bytes of memory are freed and they happen to be next to another 10 bytes of free memory, then those two free holes of 10 bytes will be joined together to form a single larger free hole of 20 bytes. Now, the block allocator eliminates fragmentation because the blocks are all of the same size. Therefore, when they're freed, they're not, and they don't need to be joined with adjacent free blocks. So there's no fragmentation, and there's no CPU usage to do this coalescing of adjacent free blocks. There's also less overhead in the block allocator because each block is a fixed known size, so there's no need to carry that additional metadata. In other words, the size of that free hole. We know what the size of the free hole is because every free hole in the block allocator is exactly the same size. So again, on a 32-bit system, that's going to free up 4 bytes of memory per free hole. And then the block allocator is also faster on allocations, whereas the list allocator needs to walk that chain of pointers trying to find a free hole that's large enough to satisfy the allocation request. The block allocator doesn't need to walk a chain at all. It always just plucks the first free hole off the front of the list and returns that pointer to the application. There's no need to walk the list because every free hole is exactly the same size. So the block allocator tends to be used in applications that allocate a large number of small objects of the same size. So all the objects are the same size, but you don't necessarily know how many of them you're going to need. So you still want the advantages of dynamic memory allocation, but you don't need the flexibility of being able to allocate widely varying sizes of chunks of memory. So typical examples would be small scalar values that are used, such as timestamp value pairs that could represent sensor data. And as I said, in an in-memory database, our database pages are small, especially compared to database pages in disk-based databases. And again, they're of a fixed size. Every database page is exactly the same size. So that makes the block allocator ideal for allocating database pages for an in-memory database. So the idea behind the block allocator is really very simple. The allocator is given a quantity of memory that we'll call a large block, and it divides it into equal-sized pieces and then organizes those into a linked list of free elements. So to serve a request for memory, the allocator returns a pointer to one free element and removes it from the list. When there's no more elements in the free list, then you can go get a new large block of memory from the memory pool using some other allocator, for example, a list allocator. And then that new large block, again, gets divided by the block allocator into equal-sized elements. And then these elements are put into a new linked list, and the allocation requests are then handled from this newly created list. With a thread local allocator, each thread has its own block allocator. So as long as all the objects are allocated and deallocated locally, in other words, by the same thread, this allocation, or this algorithm rather, doesn't require any synchronization mechanism at all, because again, the other threads have their own block allocators with their own linked lists. But then what happens when objects are not local? In other words, when memory is allocated by one thread, but then later on freed by a different thread. So in this case, the memory manager maintains what we call a pending free request list, or a PRL, for each thread. So when an object allocated in one thread is being deallocated by another thread, that deallocating thread simply links that object into the appropriate PRL list. In other words, the PRL list of the thread that originally did the allocation. So, of course, the PRL access has to be protected by a mutex. So if you've got one thread putting an object into a PRL of a different thread, we've got to protect access to that PRL so both those threads aren't trying to use it at the same time. And we do that for the same reason that malloc's chain of pointers is protected. We need to preserve the sanity of that shared resource, of that shared metadata. And then each thread is going to periodically deallocate the objects in its PRL all at once. So it's going to lock the PRL, go through the PRL, and actually free up that memory. So when does that occur? Well, it could be done using a timer, so you might just wake up every few seconds and go clean up the PRL. Or you might do it after some number of objects have accumulated in the PRL. So when you've got 100 objects in the PRL, go free them up and make them available for subsequent allocation requests. Or you might do it based on the aggregate amount of memory that's accumulated in the PRL. Say when you've got 1K or 10K of memory accumulated in the PRL, go clean it up and return it back to the pool for subsequent allocation. It's important to note that regardless of what your criteria is, the number of synchronization requests on the PRL are going to be reduced significantly relative to the number of synchronization requirements for a standard list allocator like malloc. First of all, the objects are often freed by the same thread that allocated them, and in that case, we don't need any synchronization whatsoever. And then secondly, even when the object is deallocated by a different thread, it doesn't interfere with all the other threads, but only with those threads that need to use the same PRL. So for example, let's say we've got 8 threads running, and we know from our application's data usage pattern that memory that's allocated by thread number 1 will only ever be used and or deleted or deallocated by thread 3 or thread 8. So let's say it's deallocated by thread 8. So thread 8 is going to want to link that object back into thread 1's PRL. So it's going to lock that PRL. And in so doing, it only interferes with thread 1 and thread 3. It doesn't interfere with thread 2 or threads 4 through 7. So we really dramatically reduced the number of synchronization conflicts by using a thread local allocator with the PRL. So here we see a diagram of the internal structures of the thread local allocators. And again, we're only showing two instances of the thread local allocator for two threads here, but if you imagine this extended out to 8 different threads, you can see how we're minimizing the number of synchronization conflicts across the different threads based on what our access patterns might be. The thread local allocator can create an arbitrary number of block lists of varying sizes. So in my example here, the allocator's got a 32-byte list, a 64-byte list, and a 512-byte list. But you can choose any number of lists and any number of sizes of blocks in those lists that suit your application's access pattern. So to satisfy an application's allocation request, it's going to look at the size of that allocation request and decide whether or not to satisfy that allocation request out of the 32-byte list, the 64-byte list, or the 512-byte list. And again, if all the 3 blocks in the 32-byte list, for example, are exhausted by one of the threads, you can always use malloc to go get another large chunk of memory and create another 32-byte block list and start satisfying those allocation requests out of that new list. So to the applications, the allocator exports 3 functions that have a syntax that's very similar to the standard C runtime allocation APIs. So we've got thread malloc, thread realloc, and thread free. And for applications that are written in C++, the memory manager's interface also includes a simple way to overload the new and delete operators, so you can use the thread local allocator transparently in your application code to transparently to the standard new and delete, that is. So we wrote 2 tests to examine the impact of the thread local memory manager. The first of these tests is really a best case test. So it compares the performance of the thread local allocator and the standard malloc when the allocation pattern is thread local. In other words, all the allocations and deallocations are being done by the same thread. So the same thread that allocated the memory is deallocating the memory. And then the second test is really the worst case scenario for the thread local allocator. Every single deallocation is being done by a different thread than what did the original allocation. So for the first test, the best case test, we ran this on a Sunfire X4450 with a 4 6-core Xeon processor, so a total of 24 cores, running at 2.6 gigahertz. Not sure that really matters, but and then on that system, we did in each thread 10 million allocation and free pairs in each of 24 threads, so a total of 240 million allocation and free pairs. And again, spun up 24 threads, so we were able to use all 24 cores. And again, these are all thread local, so there's no synchronization conflicts whatsoever. So all 24 threads were able to execute on all 24 cores, and we kept the system 100% utilized. So the thread local allocator executed this test in just slightly under a second, and standard malloc took over 653 seconds to run the same test. And the reason is because standard malloc doesn't know anything about the fact that all these allocations were thread local. Standard malloc is always going to protect it. It's metadata regardless, because it doesn't know anything about your application's allocation and deallocation patterns. So here you dramatically see the cost of those synchronization calls, the calls to get the mutex. Now the other test, which again is kind of the worst case test for the thread local allocator, every single deallocation is being done by a different thread than did the original allocation, so the deallocating thread is always having to lock the PRL and put the object into the PRL of the original thread that did the deallocation. So again, we did 10 million allocation free pairs, but this time we only did it with 2 threads, which, well, it says on the slide it says 2 cores, but in effect it really only utilized 1 core most of the time. And that was because we were always having to lock that PRL of the deallocating, or of the thread that did the original allocation. So we got about 15% performance improvement using the thread local allocator versus malloc in this case. That 15% is largely attributable to the superior performance of the block allocator relative to standard malloc. Again, the block allocator doesn't have to walk a list of pointers. It just plucks the first object off the list and returns it to the application. And also on the deallocations, it doesn't have to spend time trying to coalesce adjacent free blocks. So there's just built-in efficiency for the block allocator that we use within the thread local allocator. And we get a little bit of advantage off of the PRL, but again, we're only running 2 threads here, so it didn't amount to a whole lot. So in reality, your application is going to have a mix of what I've called local and global allocations. So the performance advantage of the thread local allocator is going to be a function of what the ratio is of local allocations to global allocations. It's likely to be far better than the 15% that I showed in our worst case example, but also probably not as dramatic as the 653-to-1 performance advantage that I showed you in our best case example. In other words, your mileage may vary. So our implementation of the thread local allocator, the block allocator that sits underneath it, and the 2 tests that I just described are all at the URL that's on the screen here, and Ted just put it into the chat window. You can either click on it there or just copy and paste it. On that page, there's a very simple agreement that says we disclaim any responsibility for how you decide to use this. There's no registration requirement, so we've just put this out there in the public domain, completely open source. It's not even subject to any of the various public licenses out there. So if you think it might be useful to you, you're more than welcome to download it and give it a test drive. All right, on to our second example here. So applications that have to manage some shared data face the same issues that we just described for malloc. That shared data has to be protected. Now, pessimistic locking is the usual way that developers do that. For example, through a mutex or a semaphore, or if there's multiple processes involved, then coordination with some sort of external lock arbiter or lock manager. Pessimistic locking, regardless of the granularity, acts as a prohibitor of concurrent access. Anytime you lock something, you're blocking other processes from accessing at the same time, so they're going to go into the kernel's waiting queue. So it's a prohibitor of concurrent access. If the shared data is a database, then the database is going to provide that synchronization for you, much like malloc does underneath the covers. If the shared data are simply global variables or some bit of data created in a shared memory region, then your first instinct is likely to be to implement some sort of pessimistic locking yourself, like I said, a mutex or a semaphore. And here also there can be varying levels of granularity. You can have one mutex to protect all the shared data, or you can somehow segregate it and have multiple mutexes to protect different pieces of shared data. So most programmers have some familiarity with database systems. I certainly do. So we're going to use the familiar vernacular of database systems. In other words, the database, the table, and the row to illustrate our concepts here. So the diagram on the screen here shows 3 tables in a database, each with 5 rows, and 3 tasks on the bottom that are reading and or modifying certain rows of certain tables, each within its own transaction. So for the purposes of our discussion here, let's assume that the 3 tasks all begin their transaction at approximately the same moment in time, but in order of task 1, then task 2, and then task 3. So task 1 is modifying table 1's row 3, or what I'll call T1R3, and table 2's row 5, or T2R5. And then task 2 is modifying T3R1, T3R3, and T3R5. And then lastly, task 3 is reading T3R3 and modifying T1R5 and T3R2. So note that there's 2 tasks that are working with T3R3, or table 3, row 3, both task 2 and task 3. Task 2 is modifying it, task 3 is reading it. So with pessimistic locking, there's three possibilities for the granularity. We can do database locking, just lock the entire database. We can do table level locking, and we can do row level locking. Each of these is going to exhibit different degrees of parallelism. So for database locking, we're going to task 1 and task 2 and task 3 are going to be serialized. So in other words, task 1 is going to get granted access to the database because it started its transaction first, and then transaction 2 or task 2 and task 3 are going to be blocked while they wait their turn to use the database. When task 1 completes its transaction, then task 2 is going to run, and then task 3 is going to continue to wait, and then finally task 3 is going to get to run after task 2 completes its transaction. With table locking, task 1 and task 2 can run in parallel because task 1 acquires locks on table 1 and table 2, while task 2 acquires locks only on table 3. So in this case, task 3 is going to block until both task 1 and task 2 complete, because it also needs a lock on table 1, which is locked by task 1, and it needs a lock on table 3, which is locked by task 2. So task 3 is going to be blocked for the length of time required for either task 1 or task 2, whichever is greater. Task 3 can't begin its transaction until both table 1 and table 3 are available. In other words, it can't acquire a lock first on table 1 and then later on table 3 when it becomes available, or vice versa. It has to get those locks together in order to avoid the possibility of a deadlock. And then lastly, we can look at row level locking. So again, task 1 and task 2 can run in parallel because they operate on different tables and therefore on different rows. And then task 3 is going to block because task 2 has a write lock on T3R3, which task 3 wants to read. This time, however, task 3 is only blocked by task 2. It doesn't have any conflict with task 1 at the row level. So to get around this blocking that's required because you have different tasks that want to use the same resource, regardless of what your locking granularity is, you still have the possibility of contention for the shared resource. We can use a strategy called MVCC, or multi-version concurrency control. MVCC allows all three tasks to run in parallel, even though they're accessing the same things in the database at the same time. So MVCC is what we call an optimistic concurrency model, in which no task or no thread is ever blocked by another, because each is given its own copy or its own version of the objects in the database to work with during its transaction. And that's where the name comes from. Each task gets its own version of the object in the database to work with, hence the name multi-version concurrency control. And then when a transaction is committed, that task's copy of the objects that is modified are put back into the database. So because there's never any explicit locks required, no task is ever blocked by another task that has locks, because there aren't any locks. Therefore, MVCC can provide significantly faster performance in write-intensive applications. In other words, those in which the data has to be changed very often, and with many tasks running on multiple cores. When tasks want to update the same data at the same time, then a conflict arises, and a retry is going to be required by one or more tasks. But an occasional retry is far superior to the guaranteed blocking of pessimistic locking. In other words, the theory is that an occasional retry is less expensive on the whole than always having to do pessimistic locking at any level of granularity. Also, we assume that conflicts are going to be infrequent because of the logical separation of duties amongst the tasks in most systems. In other words, task A tends to work with a different set of data than tasks B, C, D, and so on. Now, MVCC is similar in concept to read, copy, update, or copy on write and software transactional memory. The difference is that these systems don't necessarily know anything about transactions. Certainly copy on write and read, copy, update don't know anything about transactions, and the need to coordinate multiple updates across different areas of, for example, a database. All right, so my next few slides, I'm going to show you the performance difference between pessimistic locking and the optimistic concurrency model of MVCC. Too many C's in there. MVCC. So the red line is MVCC. The blue line labeled MRSIV is our pessimistic locking transaction model. It's an acronym for multiple reader, single writer. So in short, MRSIV is locking the database. So that's the level of granularity that we're talking about here. Not table or row level, but the entire database. So in this case, we're showing read-only operations. So we're just iterating over a cursor. Read-only operations can't conflict with each other because no task is actually modifying any data. So even with a pessimistic strategy, all the tasks can run in parallel because there's no interference. So the MRSIV transaction manager is extremely lightweight. Remember, we're just locking the entire database. We're not trying to do complex log arbitration at the table level or the row level. So it's a very simple transaction manager, very lightweight, and performs really, really well in certain situations because there's no complex logic there. So MRSIV outperforms MVCC from the start and right on through all the way up to 20 cores. And its performance advantage gets greater and greater as we run more cores, or run more threads rather. And the reason for that is that MVCC just has more overhead. It's a more complex concurrency model. With MVCC, we have to make copies of objects and then either discard those copies or merge those copies back into the database if they were modified. Now, in this read-only example, they weren't modified, but we still have to make copies of objects and then discard or vacuum those objects up when they're no longer being used. So there's just more overhead involved in MVCC, and the more threads you got going on, the more stuff MVCC has to do is creating more versions of objects and doing more vacuuming and whatnot. So in this, for read-only, if your application is predominantly read-only, then you probably benefit from the MRSIV transaction manager versus the more complex MVCC. But when we start talking about inserts, updates, and deletes, the picture changes. So when the database is being modified, in other words, it's not read-only anymore, then any serialization is going to effectively defeat a multi-core system. All but one core is going to be idle with respect to the utilization of that shared resource, the database in this instance. So of the three, inserts are the least resource intensive. Deletes are more resource intensive, and then updates are absolutely the most resource intensive. So inserts, which is the least resource intensive, MVCC has an advantage over MRSIV right away. And then for updates, which I said, this is the worst case for MVCC. For every update is basically a delete and then an insert. If you think about it in simplistic terms, we have to locate the object that we're going to try to update, discard that object, and then update it with, or replace it with a new object, which is effectively an insert. It's a little more complex than that, but again, for simplicity's sake, we'll describe it that way. So in this case, MVCC's got more work to do. So we need to get some number of threads going at the same time in order for the greater resource usage of MVCC to be overweighed by the greater concurrency of MVCC. And in this example, that crossover point was at 4 threads. So from 4 threads and up, MVCC is a better choice. For three threads and anything less than that, MRSIV was a better choice. And then lastly, the deletes. So similar to inserts, they're not as resource intensive as updates. So MVCC had an advantage right away, and again, that advantage was sustained throughout the run from 1 to 20 cores. Let me back up just 1 second. So you probably noticed that the performance for the MRSIV transaction manager was essentially a flat line for all 3 tests, for inserts, updates, and deletes. And the reason for that is the database locking. So it really doesn't matter if there's one thread running or 20 threads running. ExtremeDB in this example was able to affect about 500,000 rows per second. And it didn't matter if one thread was doing 500,000 rows or 20 threads were working together to insert, for example, 500,000 rows. Either way, because of the database locking, it was able to affect about the same number of rows. So what we've seen here is that database locking exhibits virtually no overhead, the simplicity of the immersive transaction manager. So when the access is read-only, it scales very well because each additional thread is able to run full speed, whereas MVCC imposes additional overhead with each new thread. It has to make more versions of objects and more vacuuming and whatnot. But when the access is read-write, then the pessimistic locking really prohibits performance from improving with additional cores. And that's what you're going to experience if you use a mutex to protect shared data. Again, unless you start segregating the data and do more granular synchronization of that data. So MVCC has greater overhead, so the performance for read-only operations is never going to match the immersive, but the greater concurrency for read-write operations quickly outweighs that additional overhead. All right, wrapping up here. So remembering that our goal is to get the most out of every core, you want to be wary about how black box components like malloc or even a database management system can get in the way of your goal. In some cases, you might have to break your old ways of thinking, such as the assumption that the standard C library functions are always your friend, because they may not be. So with that, I'm going to hand it back over to Ted. We have a few minutes here for a question and answer session.
Thank you, Steve. And yes, now we'd like to take some questions from the audience. On the lower right corner of your screen, you should see the letters Q&A. If you don't see those, look in the upper right corner and click on the button for Q&A with a little question mark over it. And be sure to maximize the Q&A on the lower right corner by clicking on the triangle next to it. That'll show you the window to enter questions. So I'll wait a moment for any questions to come in. And one question we have is it difficult to port an application from a locking transaction manager to a MVCC mechanism?
All right, so I can really only speak to our database product, ExtremeDB. There's a lot of databases that implement MVCC, Oracle, and PostgreSQL, for example. But with ExtremeDB, the transaction managers are manifested in two different libraries. So there's a library that contains the immersive transaction manager, and there's a library that contains the MVCC transaction manager. So which transaction manager you're going to use is just a matter of deciding which library you're going to link in. The application code itself just begins transactions and commits transactions, and they don't have to worry about which particular transaction manager is being used, with one exception, and that is, as I mentioned in the presentation, with MVCC you can get conflicts. You can have two tasks that try to update the same object at the same time, and the first task to commit the transaction will succeed. The second task to commit the transaction, the database runtime will recognize that the version number of the underlying object in the database changed, so it'll return a conflict error back to that second task. So the easy way to deal with that is to put your transactions into a loop. So at the top of the loop, you begin the transaction, you work with the database. At the bottom of the loop, you commit the transaction, and if the commit code comes back okay, you exit the loop. If the commit code comes back conflict, then you just go back to the top of the loop and you retry the transaction. But as I said, that should be a fairly rare occurrence. So if you write your code that way, then you can relink your application with either immersive or MVCC transaction managers, and your application code is going to be completely unaware of which particular transaction manager is being used, and then you can just experiment and see what the effect is on your application's performance with the two different transaction managers and decide which one you're going to use.
And someone has asked if it would be possible to get a copy of the slides after the event. The answer to that is yes. We will contact you with a copy of the slides. Another question that has come in is, how does MVCC handle deadlocks?
So MVCC, again, is a optimistic concurrency strategy with no locks. So with no locks, there's no possibility of a deadlock. So it doesn't have to handle it. It just can't happen.
Since neither one is blocked, what happens when two concurrent tasks modify the same data?
Yeah, that's what I just walked through in the answer to the previous question. So if task 1, task 2 try to modify the same object at approximately the same time, the first of those two tasks to commit the transaction succeeds. The second one gets a conflict error and needs to retry that transaction.
If I use a thread local allocator, does it replace malloc everywhere in my application? Is there any reason to keep malloc for some memory allocation when I'm using the custom allocator that you describe in my application?
All right, so you don't have to use the thread local allocator exclusively. You can use the thread local allocator and standard malloc within the same application. And one reason that you might want to do that, well, two reasons you might want to do that. You might want to use malloc to create your large chunks of memory that the block allocator is going to divide up into smaller fixed-size blocks. And then the second reason is you might want to use malloc if you have an allocation request that doesn't really fit into the block allocator. So in my example, we had 32-byte lists, 64-byte lists, and 512-byte lists. If for some reason you needed to allocate 712 bytes, well, the thread local allocator wouldn't be able to do that because its largest block size is 512. So in that case, you'd want to go to malloc and ask malloc for your 712 bytes.
Additional questions? I guess this refers to MVCC. Has there been any issue like data consistency being violated? No,
that's a fundamental covenant between database systems and the users that the consistency of the data always has to be preserved. And it's part of what we call the ACID properties. So ACID is an acronym for atomicity, consistency, isolation, and durability. Atomicity is that all-or-nothing property. So a transaction can modify a lot of different objects in the database, but those modifications all succeed together or none of them succeed. So the transaction is atomic. Consistency means two things, really. That applying a transaction to the database moves the database from one consistent state to another consistent state. So there's never any inconsistent state in between. And then the second meaning of consistency is that all threads have a consistent view of the database, which simply means that a task that's in the middle of a transaction, its changes can't be seen by any other task. Tasks only see committed changes to the database. And that's very closely related to the isolation property, so that changes that I'm making within a task are isolated to that task and not visible to any other task until that transaction is committed in the database. And then lastly, durability is the property that says once the database runtime gives you an OK return code or a success return code from transaction commit, that transaction is durable. It's permanent. It won't be rolled back after that.
Another question that's come in is, it sounds like MVCC helps not only multi-core and embedded applications, but will improve all multi-threaded applications. Is that correct?
Yeah. So it really doesn't matter if it's a single core or a multi-core system. You're going to get a benefit from MVCC. You'll get more benefit from a multi-core system, but you'll still benefit from MVCC on a multi-core system if you have a preponderance of read-write transactions to read-only transactions.
and I guess this can be seen as somewhat related. Is MVCC used only in databases, or is it relevant to other software applications?
Well, the concepts are certainly relevant. As I said, MVCC shares some attributes with software transactional memory, with various copy-on-write strategies. They go a bit beyond those, but the core concepts are very much the same.
All right. Are there any additional questions? It looks like we've come to the end of our session, but for any questions we haven't been able to answer, we'd be happy to respond to you by email. Just contact McObject at the email address given on the screen. And thank you for attending this webinar today. We hope you've gained a good understanding of how conflict over a shared system software resource can inhibit performance for multi-threaded software on multi-core CPUs. The two solutions discussed today, multi-version concurrency control and custom thread local memory allocators, share a common approach of dividing the resource, giving each thread or task its own copy, and, when needed, efficiently merging or passing results to the next user process. Hopefully, this general approach can be employed in other instances of resource contention. I'd like to invite you all to visit our website for the many excellent white papers, links to articles, and replays of this and other webinars available there. This webinar should be available in the next 48 hours. We'll be holding follow-on sessions in upcoming weeks and look forward to you joining us there. Thank you and good day.